Respected sir, we are Group 16 are here to present the second part of our project. I am Alaksandan Gogoi and my roll number is EAB15012.
I am Honorable Doctor and my roll number is EEB15014.
I'm Surjanam Loskar and my roll number is EEB15015.
In this video, we will be showing how we have designed our circuit and what type of input we should give to our circuit. Also, we will check the different types of output at different stages of the circuit. The IC that CD4046 that we are using is based on PLL theory. In PLL theory, the system processes until the FM signal and the VCO output are locked with each other. Also, we will get the demodulated output at the output of the loop filter, which is directly proportional to our message signal. So now let us see what type of input signal we should give.
So starting with the input FM signal, for which we have used Syntec 415 function waveform generator. First we see the carrier signal, which we take of high frequency, let's say 27 kilohertz, and we set the amplitude of 1 volt VPP, and we change the function to square wave. Now we set the duty cycle of 50%, as we know that the duty cycle of CD4046 is 50%. Now we move on to the modulation part. At first we set the type to FM signal and the shape to sine, and source is internal. And we set the FM frequency of 1 kilohertz and frequency deviation of 15 kilohertz. Now let's see the output. We are seeing it on a DSO. Now we can see that the output is clear FM. Now if we decrease the frequency deviation, we can see we are unable to see the deviation between the frequencies in the FM. So we go back to the 15 kilohertz of frequency deviation. So this is how we set the input signal.
Now we have to design our circuit. As our input FM signal carrier frequency is 27 kHz, we have to design our circuit that is choose our components in such a way that the output frequency of the VCO of the IC should be nearly equal to 27 kHz, so that the PLL take less time to lock the input frequency and VCO output frequency. The formula for minimum output frequency is 1 by R2 into C1 plus 32 picofarad, and maximum VCO output frequency is F minimum plus 1 by R1 into C1 plus 32 picofarad. We choose the resistance connected to pin number 12 as 100 kilo ohm, the capacitance connected between pin number 6 and 7 as 2 nanofarad, and resistance connected to pin number 11 as 10 kilo ohm. Putting this in the formulas, we get minimum frequency as 4.91 kilohertz and VCO maximum frequency as 54.13 kilohertz. We know that center frequency is half of the maximum frequency, so we get it at 27.065 kilohertz. So we connect 10 kilo ohm at pin number 11 and 100 kilo ohm at pin number 12, and both are grounded. The capture range, that is the frequency range up to which the circuit will work, should be very high. So we choose a low pass section connected between pin number 2 and 9 in such a way such that we get capture range very high. We choose resistance and capacitance of the low pass filter as 10 kilo ohm and 0.01 microfarad. By the formula for time constant, we get time constant is 0.1 millisecond. The capture range frequency formula is 1 by time constant into root over 2 pi FL by time constant, where 2FL is the full VCO frequency range, which is maximum frequency minus minimum frequency of the VCO, that is equal to 22.144 kilohertz. We get capture range is 8.341 megahertz. At the demodulator output terminal, that is at pin number 10, we connect a second order low pass filter circuit of capacitance value 0.01 microfarad and resistance value 10 kilo ohm. and the load resistance of 10 kilo ohm is connected, which is further grounded. So as you see in the pin 14, we give our frequency modulated signal, which we have to be demodulated. Pin number 3 and 4 are shorted. In pin number 16, we give the DC voltage of 5 volt to operate the IC, and pin number 5, that is the inhibited, and pin number 8 is connected to ground.
So this is the input FM signal at IC pin number 14, which we have to demodulate using our demodulator circuit. And this is the input to the phase comparator 1, which is of exclusive OR gate type. We get here 1 volt peak to peak amplitude signal, but due to some noise we can see that the amplitude has changed to 1.36 volt. Now we go to pin number 3. Another input to phase comparator 1 at IC pin number 3, which is also the VCO output. Here we can see that we get a signal of 5 volt peak to peak, which is the input DC volt given at pin number 16. At pin number 2, this is the output of the phase comparator at pin number 2 of IC. After low pass filtering this signal, we get this charging and discharging type of sinusoidal signal, which is also the VCO input at pin number 9. Now we check the signal at pin number 7. We get this type of signal after passing through 0.002 microfarad. So we have seen that the output at different stages of the demodulator circuit. Now let us see the demodulator signal at different stages of the second order LPF at pin number 10. So at pin number 10, without low pass filtering, we get this type of output which have lots of amount of noise. After the first LPF, we get the noise which is in a much reduced form. And in the second LPF, we get the final output with much reduction of noise. So as we see in the output, we get exactly 1 kilohertz frequency message signal, which was the design purpose of our demodulator circuit. And in the second LPF, we get the final output. So if we use more number of LPFs, the noise can be reduced to further extent.
This is the final module of our PCB. This is the FM signal input terminal, this is the VCC terminal, and this is the demodulator output terminal. We have set our FM signals to our desired values, and we have also given 5 volt to this input terminal. Now let us see what output we get from this terminal. When we connect this to our output terminal, we get our desired demodulated signal output, which is of 1 kilohertz.
So we see from our output observation that we get our desired modulating signal of 1 kHz frequency. The output of demodulator circuit is directly proportional to input signal's frequency. So the output signal's amplitude is high where our input signal's frequency is high, and the output signal's amplitude is low where our input signal's frequency is low. PLL FM demodulator is a FM that gained widespread acceptance in our recent years. The basic idea of PLL is a negative feedback control system. PLL FM demodulator is a high performance frequency modulator demodulator. They are used in many FM receiver applications. The advantages of FM demodulator using PLL in its linearity and its manufacturing cost. They do not require a costly transformer and can easily be incorporated within FM receivers as FM radio ICs. We can use our circuit in many applications, from broadcast receivers to high performance communication equipments. We can use our circuit in FM radios and IR headphones. CD4046 consumes only 660 microwatt of power at 10 kHz, a reduction in power consumption 160 times when compared to another PLL monolithic ICs which consumes 100 millivolt power. So we can conclude that by using our demodulator circuit, the FM wave can be demodulated. FM wave can be demodulated with greater efficiency.